little bit of an overview about the essential principles of climate literacy, and I think you all have a copy of the brochure, and some of you are familiar with it, others may be brand new to you. I'm an associate scientist at the Cooperative Institute for Research in Environmental Sciences here at CU Boulder, and we work closely with the NOAA labs down the hill and with the folks here at NCAR and colleagues all over the country here. But I'm going to give you a little bit of an overview of the essential principles of science literacy, talk a bit about the carbon cycle, because there's a lot of misconceptions that students and in fact teachers have about the carbon cycle, greenhouse effect, and so forth. I'll also share with you a little bit of some recent survey data about some of the beliefs and attitudes that the general public and young people in particular have about climate. And then we'll kind of hone in on some of the key misconceptions or naive conceptions that people may have, both teachers, the general public, and students, around different aspects of climate science. And to kind of help set the stage, John Muir had this fabulous kind of summary of the kind of the philosophy of ecology. When we try to pick anything out by itself, we find it hitched to everything else in the universe. And that's certainly true when it comes to climate and certainly life itself. So the brochure, The Essential Principles of Climate Literacy, has been several years in the making. And it went through an iterative process. The first version was actually geared for K-12 teachers. And then we did another more recent version that has the subtitle of A Guide for Individuals and Communities. And is that? Oh, here we go.
This is in your bags.
So we've expanded the scope a bit. When folks initially opened up the brochure, you'd see a matrix of how the essential principles map to the science education standards. And if you weren't a teacher or if you didn't care about the national standards, which of course a lot of folks don't care about them if they're driven more by state or district standards, then that matrix was pretty much unhelpful or even a distraction. So I think the new version is a lot more complete, and it actually went through a review by the principals of the Climate Change Science Program, which is now called the U.S. Global Change Research Program. But there were 13 federal agencies involved, and we, here's the logos of them actually. It's quite a robust group of federal agencies, and they all bought into this as a simple document for talking about the basics of climate science. And we feel like this was quite a breakthrough because there is the tendency to reinvent the wheel and create new programs that are all about Climate 101 and so forth, and that's fine, but at the same time it would be nice to have one document that was kind of officially stamped with approval from all these different agencies. And they all have something to do with climate one way or another, whether it's in the Department of Interior that former Senator Salazar now runs, USAID that is geared towards providing aid and guidance for folks in Africa and Asia and so forth, NASA, the US EPA, and the effort was largely led by NOAA, the National Oceanic and Atmospheric Administration. So there's a group called the Climate Literacy Network that was formed as we started to put the essential principles together by outside folks, people outside the agencies, including myself. Tamara Ledley at Turk is the current director. Turk is a science education facility out of Cambridge, Mass. That some of you might be aware of. And there's actually a group of people all over the country that participate in weekly telecons just to share information and look for ways that we can maximize our strengths, avoid redundancy, and really try to come up with an integrated approach to climate education, climate science literacy. And this is the website, climatelitracynow.org, if any of you are interested in learning more about the Climate Literacy Network. But we've also started to expand it. We've started working with the education group at the National Renewable Energy Lab down down the way in Golden. And we have a proposal into the National Science Foundation called the Climate Literacy Energy Awareness Network, which has the great acronym of CLEAN. It's very important you have an acronym that people can pronounce. And of course, it's about clean energy and climate, which are intimately connected. How do we define climate literacy? Very simply, understanding the influence of climate on society and ecosystems, we could say, and society on climate. And as we now know from all the research that's gone on, particularly here in Boulder at NOAA and NCAR, these two are very closely coupled, as scientists would say. The essential principles were guided to a large extent by the benchmarks for science literacy developed by the AAAS Project 2061. I know many of you are familiar with this, and I see a strand map here on the table. And there's also online versions that some of you may be aware of that our colleagues at the National Science Digital Library here in Boulder have put together with the AAAS. These are wonderful tools, online tools, where you can drill down and find resources. Also, they've done a lot of work on misconceptions that students have, and we've really benefited a lot from the research they've done about some of these key misconceptions. And you can also drill down and get to different resources that they have collected. What we'd like to do next, because you click on some of these benchmarks and you get a whole laundry list of, in some cases, hundreds of websites. And that's not always very helpful. It's like doing a Google search and then having to sort through to find what's really the best. So one of our intentions is to go through a review and annotation process, bringing teachers together with climate scientists to really pick out the cream of the crop. And we have funding for that. So if any of you are interested in working in some of our boot camps, probably starting next year, next summer, there'll be like 2-week boot camps where we come in for a very intensive period of reviewing resources, some of which we've already collected, but there may be new ones that are out there that we haven't discovered yet. And then having discussions with other teachers, with scientists, and really trying to identify the very best resources about particular misconceptions or particular aspects of climate science. There are 7 essential principles of climate literacy, and we have a new online course that the Division of Continuing Education here at CU Boulder has recently launched, that myself and Dr. Sarah Wise have run this past summer. And we dig down into the science, teaching ideas, and also assessment strategies for the fundamental concepts that kind of nest down under each of these essential principles. We've also developed a handbook, a climate literacy handbook, which is on the Encyclopedia of Earth. So if you do a Google search on climate literacy handbook, it'll pop up very quickly. This is like an annotated version, an online version of the brochure there. And I think from the feedback we're getting, it's a resource that that will be really helpful because it points to other articles, other activities, resources at NCAR, at NASA, and so forth. And of course, this will continue to evolve over time. But we're very pleased that we were able to collaborate with the Encyclopedia of Earth, which is based at the University of, or Boston University, rather. I was going to say the University of Boston, but there's no such thing. So let me just quickly walk through the 7 essential principles. The first being the sun is the primary source of energy for the Earth's climate system. And as we're discovering, this is the one that probably gets people tripped up the most. There are lots of misconceptions about this particular one. And in our online course that we've been running, it was really interesting to have teachers who thought they knew what the greenhouse effect, how it works and so forth, describe how they thought it worked. And it was very clear that they had misconceptions themselves that they were perhaps passing on to their students. The other thing we recognize from our work on misconceptions and general confusion that people have about climate science is that people can hold a misconception and a correct assumption and another misconception at the same time. And so it's really tough to recognize when people have these misconceptions, whether it's in ourselves or in our students. And so that's where we intend to put a lot of our effort is helping tease out these tripping points, if you will, so that we can develop a more climate literate society from the inside out. The second principle is that climate is regulated by complex interactions among components of the Earth system. And of course, a classic example of this is El Nino Southern Oscillation, El Nino, La Nina, and the sort of the chaotic pulse, if you will, between those. There's experts here in Boulder that study this in a lot of detail because it has ramifications for hurricanes in the Caribbean, precipitation in different parts of Colorado, different parts of California, in different parts of Asia. So there's a lot that's still not understood about how these oscillations are driven, and trying to predict them can be very, very challenging from one year to the next, from even a couple of months in advance. The third essential principle is that life on Earth depends on, is shaped by, and affects climate. Microbes have been impacting climate for literally billions of years. Plants, as they pull carbon dioxide out of the atmosphere, are having an impact on the amount of CO2 in the atmosphere on a seasonal level. And that has very subtle but perhaps significant impacts on regional climates. And certainly microbes are continuing as, for instance, the permafrost begins to melt in the Arctic and biologic activity starts to emit methane. That's contributing to the changes in the climate system there. The fourth essential principle is that climate varies over space and time. As I'm sure you've already seen, a lot of these essential principles overlap. And at times it's important to kind of go through in a linear fashion, but also there's a lot of linkages that can be made between these essential principles, and particularly when we start to bring in the human dimension here. I'll talk more shortly about some of the best practices that are emerging in terms of teaching about climate change, but certainly one of them is that it's really important to bring in solutions when you're talking about climate issues, so that like when we're hearing about the changes in precipitation that are likely here in Colorado or in the Sierras, one of the questions to pose is what can we do about that? Given the likelihood that this is going to be happening, what can we do to prepare? What can we do to be more water conserving? Drip irrigation perhaps instead of flood irrigating alfalfa fields for cattle and so forth. So there's a lot of interesting solutions that can be brought into the science, and we also recognize that young people in particular can be completely overwhelmed and become ecophobic, if you will, by hearing too much gloom and doom about climate change and so forth. So giving them positive actions beyond just changing light bulbs and so forth is really crucial. The fifth essential principle talks about the nature of science, the scientific process, and how our understanding of the climate system is improved through observations, theoretical studies, and modeling, and they all go together. The sixth focuses particularly on the fact that human activities are impacting the climate system, not just burning of fossil fuels, but certainly land use changes are also playing a significant role. And then the seventh essential principle is that climate change will have consequences for Earth system and human lives. And as we revise this newer version of the essential principles, it was interesting to hear from the Housing and Urban Development Agency that the folks from there, through the Center for Disease Control and so forth, are very much focused on human impacts. And this is relatively new, but they're concerned about changes of disease vectors and so forth that climate change will impact. And they were adamant that this was an important part of the essential principles, and that in fact there is good science to back it up. But all of these essential principles are kind of framed within what we call the guiding principle for an informed climate decision, which is that humans can take actions to reduce climate change and its impacts. And this again gets out of kind of the formal applied science and more into, or the formal research science into how do we apply this in our everyday lives? What are the solutions given this information that the science community is giving us? And what are the things we can do to reduce the impacts, but also what can we do to start to adapt to the changes that we're already seeing? Adaptation is something that a lot of folks have just not wanted to talk about because in some circles it felt like it would distract from the imperative of reducing carbon emissions in particular. But we also know now, particularly in the past year or so, that a lot of the changes that are already in the pipeline are going to be with us for many, many decades, centuries, as long as 1,000 years or so. So just quickly, I'd like to just summarize carbon. What in the world does carbon have to do with climate? A lot of us are encouraged to buy carbon offsets, use carbon calculators, et cetera, et cetera. And yet this is one of the biggest misconceptions that people have. We're talking about cap and trade, et cetera, et cetera. But what it boils down to, in my mind, and Peter Tons may have talked about this a bit yesterday, is the fact that essentially all of our food and the vast majority of the energy we consume, 86% of our energy comes from fossil fuels, comes from out of thin air, in fact. And that's the connection between carbon and climate that is often overlooked. We jump right into carbon calculators as if kids are going to be able to understand what that has to do with carbon and the climate cycle. I think it also brings in the biologic realm in a way that often we overlook, because climate is so interdisciplinary. It kind of falls between the cracks of chemistry, physics, biology, earth science, and so forth. And of course, traditionally, earth science tends to be more geology-oriented. But I think as we bring in the carbon cycle, particularly talking about how our food and energy come from carbon dioxide that plants pull out of thin air, we can really bring this alive in a way that we haven't previously. We often talk about how thin the atmosphere is, and we see these incredible pictures from the space station and so forth that really give us a sense of what a thin membrane that is. On the other hand, we're down at the bottom of an ocean of air. And we don't think of it like that too often because we're adjusted to it in our everyday lives. And again, this is one of the misconceptions that is hard to kind of break through with some of the younger learners in particular. But at sea level, that's 10 tons of air per square meter, 14 pounds per square inch, pressing down on us. But we're like fish in the ocean. We don't realize that we have all this pressure bearing down on us, and that the air surrounding us has mass. One of the first scientists to start to unravel this mystery of the connection between carbon and climate was Jean-Baptiste van Helmont, who's a Flemish scientist back in the 1600s, who was very curious about where plants got their mass from. So he took a willow tree in a pot, and he measured the growth of the plant, and the only thing that was coming into this little experiment was rainwater. And so the plant was growing, and he deduced that the plant therefore must be gaining its mass from water. And of course that's a common thought that many students have. He also, interestingly enough, was the first scientist to use the term gases. Before that it was just air, but he began to think that air is made up of different stuff. And so he didn't quite have the full picture, but he was beginning to unravel the story. And not too long, a couple generations later, John Tyndall, who was a British scientist in the mid-1800s, was starting to do some back-of-the-envelope calculations, if you will, about the energy balance, incoming radiation from the sun, the outgoing radiation from the Earth after it's been warmed by the sun. He knew that they were different. He knew that the incoming was shorter wave radiation, the outgoing was longer wave, what we call infrared radiation. And according to his calculations, the math didn't work out because we should be colder than we are. And this is way before computers. He was doing all this hand calculations. And so he deduced that there must be some kind of amplified warming that was in effect trapping or absorbing some of that heat, that infrared heat coming off the surface of the Earth. So this helped set the stage for what we now call the greenhouse effect. And what he did, this is a few years later when he was Sir John Tyndall, he set up a laboratory in the basement of the Royal Institute and began, it was like a mini atmosphere, and he began testing different gases to see which ones absorbed infrared heat. And he published this in the 1860s, or 1872 actually. He did a lot of his research in the 1860s. Contributions to molecular physics in the domain of radiant heat. And he focused on two particular gases which he determined absorb infrared heat, carbon dioxide and water vapor. These are what we now call greenhouse gases, really incredibly important to the understanding of the balance. We now know what he intuited and observed from his experiments, that 99.9% of the atmosphere does not capture heat. Nitrogen, oxygen, argon that absorb, that make up 99.9% of the gases don't absorb that infrared heat. But some of these so-called trace gases do. In particular, he looked at carbon dioxide and water vapor, but methane is another important one, and we now know that there's some gases that didn't even exist during his day, man-made gases, refrigerants in particular, that absorb that infrared heat. Without the greenhouse effect, liquid water just wouldn't exist. So the greenhouse effect is in fact a good thing. We'd be a frozen snowball in space if it weren't for this amplified warming that John Tyndall focused on. And today, of course, through satellite measurements and so forth, we have extremely detailed mapping of the incoming radiation, how much is reflected, absorbed, and so forth. And the key part of the equation when we talk about heat-trapping gases and so forth are these the gases, the amount of radiation, infrared heat absorbed by the atmosphere by these particular gases. Satellite measurements since the 1970s give us a very, very detailed picture of how much is reflected, how much is absorbed, how much is then radiated out from the surface of the Earth, both land and ocean. And water vapor, yes, is a very important greenhouse gas, but it's in the atmosphere only about 9 days. So that it absorbs heat, but it also releases heat very quickly. And yes, it's an important gas, but also there's a sort of a cooling effect when water is evaporated. So the water part of the equation is complex and important, but again, compared to some of these other longer-lasting greenhouse gases, it's quite short-lived. Carbon dioxide is invisible, odorless. We can see it in the bubbles in our soda. And of course, coal is kind of the ultimate example of carbon in many respects. Well, maybe a diamond is the ultimate example, but you know, a coal was created through that whole carbon cycle process of plants pulling carbon dioxide out of the atmosphere, then through geologic processes that the carbohydrates are transformed into hydrocarbons. And then when we burn the coal, it releases carbon dioxide into the atmosphere. One of the scientists, generation after John Tyndall, Svan Arrhenius, got curious about what if we kept burning coal. They were burning a lot of coal in Sweden and in other parts of Europe at the time in the late 1800s. And so he did a bunch of mathematical calculations, again by hand, published in 1896 on the influence of carbonic acid in the air on the temperature in the ground, and he deduced from his calculations that eventually the Earth would warm, the atmosphere would warm from the burning of fossil fuels. He thought it would take a long time, though. Fast forward to International Geophysical Year, 1957, 1958. The National Academy of Sciences published a series of these posters, which are up and down the hallways here at NCAR. They're really quite interesting and beautiful posters. And you'll see little numbers on there. The numbers refer to a little booklet. One of the posters is on weather and climate, and this little booklet is called Planet Earth, The Mystery with 100,000 Clues. Both of these, the posters and the booklet, are available for download if you do a Google search on NAS IGY posters, NAS for National Academy of Sciences. And they're wonderful artifacts of the state of the science 50 years ago. And in the chapter on weather and climate, where they're talking about the greenhouse effect and the incoming shortwave radiation, and then the longer wave infrared being captured by water vapor, carbon dioxide, and so forth, they note that our industrial civilization has been pouring carbon dioxide into the atmosphere at a great rate. By the year 2000, we will have added 70% more carbon dioxide to the atmosphere. If it remained, it would have a marked warming effect on the Earth's climate, but most of it would be probably absorbed by the oceans. Now, today, we know that maybe 30% of it is absorbed by the oceans. Conceivably, however, it could cause significant melting of the great ice caps and raise sea levels in time, and in fact, that's exactly what we're seeing today. Sea level, by the way, is not necessarily uniform around the world. There's a wonderful NOAA website on tides and currents where they show that globally there's sort of bulges of sea level in certain parts of the ocean, and in other places it's actually dropped down. So when we talk about global sea level rise, there's places where the sea level will definitely rise, such as the Gulf Coast of this country. In other places, in parts of Alaska and Greenland, especially as the glaciers melt and the land kind of rebounds from all the pressure on top of it, there may be actually the reverse effect. And that NOAA website is a good place to get more information about that. But that sort of encourages us to think of sea level in a different way than we're used to thinking of it. So in the past 50 years, the population of the planet has more than doubled, and it's expected to continue to grow. Obviously, human population is an important part of the equation, and the use of that population, how much fossil fuel is this added population going to be consuming, is another part of that equation. And since the 1950s, we've seen the amount of fossil fuel carbon emissions go from somewhere around 3 gigatons a year to, it's actually closer to 9 gigatons a year, and it's heading towards 12 at the rate we're going. We've also seen from the work that Peter Tons and others have done at NOAA and with this global CO2 monitoring network, the CO2 emissions rising. By the way, this is a program started during the International Geophysical Year in 1958. And we also see that little bump in the annual cycle as all the plant materials in the Northern Hemisphere absorb some CO2 for photosynthesis in the spring and summer, and then through decay, some of that carbon is put back into the atmosphere in the fall and winter months. So 20 years ago, Harvard University did a study that I'm sure a lot of you are familiar with, the Private Universe study, and they asked a couple of tough questions about the phases of the moon and the reason for the seasons. And this is my personal favorite. A seed grows into a large tree, and they often are holding a log and asking, where did the mass of the tree come from? Where did the mass in this log come from? And then they say, well, what if often they say, oh, I just don't have a clue. These are graduates from Harvard University who don't have a clue. Because somehow or other, in 16 years of the finest education in the world, they never learned the basics of the carbon cycle. Some of them actually could spout about the photosynthesis process and the Kelvin cycle and so forth, but they still didn't really understand that the mass of the tree comes from carbon dioxide essentially pulled out of the air. And when they were told that, some of them said, I would be very disturbed if I learned that that was the case, because it was not intuitive. So I think, again, just to emphasize this, I think this is an important piece of the puzzle that as science educators we need to revisit, because if you're talking, for instance, about one of the solutions being biochar, where you create charcoal through a process, a reduction in atmosphere, where you can capture some of the off gases and perhaps use them as fuel, but then you can take that charcoal and bury it in the ground. It's helpful to know about the carbon cycle if you're going to actually pursue a solution strategy such as biochar. And understanding all the details of photosynthesis, this really wasn't teased out by scientists until well into the 20th century. But I think this little story about sort of the story of carbon and climate is really incredibly important, reminding people that our food, even if we eat meat, the animals ate plants at one point along the chain. It's really incredibly important that we emphasize this, because it seems to be a missing link in a lot of our education programs right now. We can talk about the various equations of photosynthesis or even combustion, but the bottom line is that fossil fuels are in effect buried solar energy, very, very concentrated forms of solar energy. 1 gallon of gasoline, it's estimated, are the equivalent of 98 tons of biomass. And so that when we open our refrigerator and we look at the food in there, that food, in effect, came from out of thin air, and the electricity powering the refrigerator likely comes from coal. So certainly here in Colorado, that's the most likely scenario. So when we think of that whole chain of events that links us to a past climate and is impacting the future climate, I think it can really help bring climate science alive. Now, before I move on to some of these key misconceptions, I want to just note that climate science is pretty much missing in action when it comes to the science standards. Certainly the national science standards, climate change has not been mentioned. Some of the states do talk about it. Very, very few of them talk about solutions. Here in Colorado, there's been a lot of revamping and revising of the science standards, and I think the version that comes out later this year should be a lot more robust in terms of climate science. Personally, I would love to see the graduation competency standard around climate and energy awareness, and I don't see that happening in this current round. But Sarah Weiss, who some of you know, a visiting fellow here at CU, did a study this past couple of years on Colorado science teachers, and found that about half of them, actually less than half, do teach climate science in their courses. Only about a third of them have ever gotten any kind of professional development around climate science. So they go to Google, they go to magazines and so forth to try to bone up and get background so that they can talk about it in their classes, because a lot of their students are talking about it. Surprisingly, only about 10% of the teachers were ever discouraged from talking about climate science. So I think that in a way is good news, because a lot of us expected that figure to be quite a bit higher. And in fact, about a third of them were strongly encouraged to address climate change. Two surveys I want to briefly mention. One is from Tony Lazarowitz at Yale University called the 6 Americas Study. And he has identified 6 demographic groups. The alarmed make up about 18%. These are folks that are really concerned about climate change. Concerned, these are folks who think it may be a problem, but it's not the top of their priority list. Cautious, another 20%, are less concerned, but it's still on their radar. The disengaged, it's definitely not on their radar. They're focusing on who knows what, video games or something. Then there's the doubtful, who may be open-minded or not. And then the dismissive are actually only about 7 or 8%. So the dismissive tend to be quite vocal and writing letters to the editor and generating a lot of heat, so to speak. But there's not a lot of them out there. And in fact, a survey was done not too long ago of scientists in the American Geophysical Union that found that of the scientists who publish about climate in peer-reviewed journals, over 97% of them think that there's a human signature on the climate change that we're observing. I'm going to skip that one, but in terms of self-assessed knowledge, those who call themselves alarmed feel like they know quite a bit, but not a lot. The dismissive think they know quite a bit, and then a lot of people just admit that they don't know much about it. Another survey done by the Ocean Project, they were focusing particularly on people's attitudes and beliefs around the ocean, and there's obviously a strong connection between the ocean and climate. They were interested in finding out people's concerns about pollution in the ocean and so forth. And they found that the ocean in general is a very, very low concern, but global warming is the #1 concern in terms of environmental topics among the people that they surveyed. And it's particularly high among young people, 12 to 13, that's 83%, 14 to 15, 87%. By the time they're in their 20s, it drops down a little bit, but even 55 to 64, it's 60% feel that climate change is a big deal. I'm sorry, this is on personal responsibility for protecting the environment. And this slide is on the importance of confronting climate change. Again, there's this big bulge of teenagers who will soon be going to college. I'm not sure colleges are ready for these young people who are going to be, pretty informed and motivated and looking for solutions, looking for programs that they can, learn about careers and solutions and so forth. I'm involved with some of the work going on at CU Boulder, and it's going to be interesting. Let's put it that way. As these young people come in, and the old school philosophy and politics of universities run into these very motivated young people. But here's something that I found really interesting in this survey, that 78% of adults say that my child is better informed about current environmental issues than I am, and that while these young people may not be decision makers, they are increasingly opinion makers in their homes. And I think, in a way, it's to your credit. These young people are learning from somewhere. They're learning maybe from MTV a little bit. But I suspect a lot of it is from all of you who, in your classrooms, are helping them understand the challenges that they're going to be facing. And so let me just take a few minutes here and talk about some of these key misconceptions. This is one that showed up in the Private Universe study back 20 years ago. A lot of folks think that the reason for summer is that we're closer to the sun, and in fact, the Earth is a little bit closer to the sun in January than it is other times of the year. The concept that it's the tilt of the Earth that is the reason for the seasons is a tough one to convey, and from the work that the folks at AAAS have done, it's really not until high school when the students have enough geometry and physics to kind of get it that they're able to really understand this particular concept. Another one that I mentioned earlier is the fact that in our everyday experience, air is invisible and weightless, and therefore it's hard to get across the concept that air has density and in effect can have momentum, as cold fronts and warm fronts and convection are all in the mix. That's part of the fact that air is not just invisible and weightless. Also, we sometimes define climate as average weather, and in terms of taking observations from weather stations and analyzing the data and so forth, there's some truth to that. But in fact, meteorological processes are very different from climatological ones, and they're studied very differently as well. How can a few trace gases warm the entire planet? 99.9% of the gases don't trap heat, but in effect you can zero them out of the equation because these other gases do absorb some of that infrared heat. And when you go from 280 to 390 parts per million of CO2, and you double methane concentrations, those do alter the equation in a substantial way. Also, we sometimes use the metaphor of it's like a greenhouse, and the air, hot air is trapped from going outside, like in a car in the hot sun type of thing. And we've been talking about this on our online course because that's often how teachers talk about it in the classroom. And that's probably okay, but then if you get into high school, college, you have to sort of undo that learning because it's not really like a greenhouse. Those greenhouse gases are absorbing, they're not serving as a blanket or a block per se. Global warming is caused by the ozone hole. When I talked to my neighbor and explained to him some of the work that I do, that was he said, well, I don't use hairsprays or styrofoam cups anymore, so he's sort of in a time warp from 20 years ago when we were trying to heal the ozone hole. In fact, I saw a study recently where as the ozone hole in Antarctica is starting to sort of patch itself up because we did ban chlorofluorocarbons and so forth, that it's changing some of the wind patterns in Antarctica, and that may accelerate the warming down there. This is a tricky one here also, just what we talked about earlier, the incoming shortwave, visible ultraviolet radiation coming in and then being absorbed by the Earth and then radiated out at a longer wavelength. And all too often when we see these diagrams, unless we kind of pay close attention and sort of deconstruct this piece, it can look like it's just reflecting off the surface of the Earth. And again, that's one of those key misconceptions that can be tough to undo. We've sometimes heard that it's just natural cycles, that the solar cycle is the reason that there's been warming going on, but in fact, we now know from these very sophisticated observations that there's only about 1 watt per meter square difference between the solar minimum and solar maximum. And yes, we've been in an extended minimum period right now, and that 1 watt per meter square, may be important. There's a lot of unknowns in this. There's actually some discussion about how during the minimum period there's more cosmic rays coming in that create more water vapor, and there's still some unknowns there, but I think overall the conclusion that the consensus of scientists have reached that human activities are warming the planet is going to be, it's going to withstand the test of time, so to speak. And it's very well verified and accepted by the science community. And then just to circle back around to the carbon cycle again, A lot of folks, adults, students, maybe some teachers, assume that plants get their mass through water and nutrients pulled up through the roots, when in fact it's through that carbon dioxide in the air. And then finally, in terms of energy, there's the misconception that energy is some stuff, when in fact by definition energy is not stuff. You know, we talk about energy companies and so forth, but when we dig coal out of the ground or pump oil out or generate energy from a wind turbine, it's that potential to do work through the turning of the generator that is actually the source of the energy. And again, to reinforce this concept that the fossil fuels are, for all intents and purposes, concentrated buried solar energy. Some students think that as we burn carbon, it's being destroyed, that we're altering the carbon cycle. Well, we're altering it in some ways, but we're not destroying it. We're just moving different parts of carbon around in a way that they wouldn't normally move. And many people not only don't know really where their food comes from, but they also don't really have an understanding of where their electricity comes from, or the fact that we burn coal to generate steam to turn the turbine to send off this alternating current down the wires that run our iPods and our computers and our lights and our refrigerators. So the final misconception I want to focus on is, in some ways, this is a very important one, and a lot of you are probably familiar with the wedges that were developed at Princeton University, and there's a wedge game that some of you may have used in your classrooms that I think is actually a really good way of helping students understand the complexity of the issues, as well as how we need multiple solutions. You know, there's no one solution that's going to fix everything. However, the fact of the matter is that it's going to be very, very tough to reduce concentrations and stabilize the growth of greenhouse gases in the atmosphere, let alone to reverse them. John Sturman at MIT had some of his graduate students put together a little concept map of what they thought would be required to just stabilize concentrations. And basically the students all said, we just need to level it off where we are today, and that'll stabilize concentrations. But the metaphor that he's come up with is the bathtub metaphor, because if there's 9 gigatons of carbon coming in per year, there's anticipated to be 12 gigatons in the coming years. That's sort of a faucet into the bathtub, and the bathtub's already at this level, and the natural drain is about 4 gigatons a year. We're going to continue raising the level of the bathtub unless we actually go backwards. And that's one of the things about this, the wedges that's important, is that it's acknowledging that we're going to have to go backwards. We just can't level it off here. And the MIT grad students didn't really get that, but hopefully your students will, as you help them understand the complexity of all this. So I think that's all I have this morning. It's getting close to lunchtime, but do you have time for a question or two?
Yeah, I think we should take a few questions. I'll just go through lunch a little bit. Well, I have a comment. Yeah. My memory is horrible, and I'm pretty sure I participated in Sarah Wise's study. Did she do it online and ask questions? Yeah. There was that 10% value at the end that said teachers weren't discouraged from teaching climate change. But my experience...
No, well, 10% have been discouraged.
Oh, only 10% have been discouraged. Right. But my experience has been, for people that I've talked to, just anecdotal, my own experiences are that I'm not discouraged from teaching climate change, per se. I am discouraged from teaching that it's caused by anthropogenic reasons. Like, my principle suggests that I notify parents ahead of time, through their student, and allow them to opt out because it's controversial. So I'm wondering if in that 10%, there's a distinction between, I can talk about climate change, it seems like, temperatures are increasing, blah, 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 but I can't talk about causes being human caused.
Yeah, I don't remember how that question was phrased, whether she parsed out the difference between the two, because that's
it seems awfully low, just from my own personal experience.
How about the experience of others of you? Have any of you been actively discouraged from talking about human contributions?
I wasn't discouraged by my administration, but I've had issues with parents.
Yeah?
Yeah.
So how do you handle it?
I was outside out.
Really?
Yeah. And actually, you weighed in on the
That's
conversation.
right. You're up in Evergreen.
Yeah.
Yeah.
And because I was desperate, I needed help. And it all worked out in the end, but it was really hard.
Yeah.
But my administration stayed behind me.
Good.
So.
Yeah, that was very intense there, as I recall. And it was a couple of very vocal students who...
Yeah, it was a group of parents, whose kids were in my class.
Oh.
So.
Anybody else have that type of experience? Any of you been encouraged by parents or your principal? So I guess one of the questions I have is how many of you do currently talk about climate change and the human impacts on the climate system? So most of you, okay. Great. So any other questions or comments? And thank you all very much, and I appreciate the shuffling of the schedule because I have to head off to a meeting this afternoon. So.
Thank you so much.